This video explores the concept of osmosis. Osmosis is one of the more difficult concepts within cellular transport for students to master. And you may recall that the definition of osmosis is the diffusion of water across a semipermeable membrane. Now, when we say diffusion of water, that means water will move from where there's more water or a higher concentration to where there's less water or a lower concentration. So let's use a scenario to try to understand the different terminology that goes along with osmosis. Let's say that we went to a carnival and we won a goldfish at the carnival at the fish toss. And we take that fish home and we put it into our tank. And let's say, for argument's sake, that we live near the ocean and we know that the ocean has fish in it and it's made up of salt water. So we take a sample of salt water and put it into our fish tank. And that salt water is a solution, which means that it's made up of dissolved substances within the water. Let's say that those dissolved substances make up about 5% of the solution, and we're going to, in general, call these dissolved substances solutes. Now, the remaining portion of salt water, which is the solvent, is about 95% water. In comparison to the fish, whose cells, when they stay within homeostasis, have 0.9% solutes, and that makes 99.1% water within the fish cells. Now, the fish wants to hang on to their solutes regardless of the environment that they're in. So in this particular scenario, water is going to want to move from where there is more water to less water if the solutes are stuck. Not all solutes are stuck, but for this scenario, we're going to say that the solutes cannot move. So we have 99.1% water in the fish and 95% water outside, so the water is going to start to move out of the fish. A little bit will still move into the fish, however, the net movement of water will be out of the fish. Now, the terminology that goes on along with osmosis deals with this term tonicity. Now, tonicity deals with the solute concentration within the solutes. And if we look at the salt water, there's 5% solutes. The fish, there's 0.9% solutes. Because there is a difference between the two, the higher solute concentration is deemed the hypertonic solution, where the fish would be considered the hypotonic solution. Hyper meaning above, hypo meaning below, and tonic referring to the solute concentration. Now, a fish in this scenario would start to have its cells shrivel and essentially die if we don't do something about it. So our fish starts to shrink and we notice it's not looking so healthy. So we're going to reset the water because we know the salt water is not good for it. And let's say, for argument's sake, we have some distilled water sitting around. Distilled water has absolutely no solutes in it. So there would be 0% solutes and it would be 100% water. The fish's concentration still wants to stay at 0.9% solutes and 99% water. Now, in this scenario, there is still a difference in the concentration of solutes and water between the two solutions. Because there is more water outside of the fish than in the fish, there will be a net movement of water into the fish. There will still be a little bit of water that leaves the fish, but the vast majority of it will be the net movement into the fish. Now, if we take a look at the solute concentrations between the distilled water and the fish, there's 0% solutes within the distilled water. There's 0.9% solutes within the fish. So when we have to use the terms hyper versus hypotonic, the distilled water is now having less solutes than the fish, so it would be hypotonic. Therefore, the fish would be hypertonic. Now, in this scenario, the fish is going to start to bloat to the point that it's going to also die. The cells can start to pop or lyse. And we want to move it into a healthier environment. So when we move the fish into a different environment, our last solution is kind of tap water. And tap water does have a little bit of solutes in the water. That's pretty equivalent to the fish, about 0.9% solutes. And that would mean about 99.1% water. The fish is still going to stay at 0.9% solutes and 99.1% water because it wants to remain in homeostasis. Now, you may sit there and think, okay, so the water's not going to do anything because the concentrations are the same. That's incorrect because water will still want to move, but it moves at an equal rate in and out. So when you have equal concentrations of solutes, you no longer have hyper versus hypotonic. You are now in a situation where the solutions are isotonic, or meaning they have the same tonicity. And again, the water is going to want to move in and out, but it moves equally, so the fish stays happy. Now, for our summary, if there is an unequal concentration of solutes between two solutions, water will always move, either towards the higher solute concentration or toward a lower water concentration. These two phrases actually mean the same exact thing. Now, if the solutes between the two solutions are the same, water will still move. It just moves at an equal pace inward and outward.